Tonight, we're going to break your sense of how fast anything in the universe is allowed to spin. Picture a dead star's core, the burned-out heart of something that used to be bigger than the sun. Now crush that core down until it's the size of a city. 20 kilometers across. Not a gentle cosmic snow globe, but a sphere so dense a teaspoon of it would outweigh a mountain. Then press play, because this corpse is rotating hundreds of times every second. It doesn't blur. It doesn't explode. It doesn't fling itself across space like a failed carnival ride. It just keeps turning. You have an intuition for spinning things. You felt it in your hands. Toss pizza dough into the air and spin it faster, and the dough stretches, thins, threatens to tear itself apart. Watch a figure skater pull their arms in and whip into a blur, or a ceiling fan rattle and wobble when you push it to its highest setting. There's always a limit. Push too hard, and gravity, friction, the strength of the material all team up to say, that's enough. So let's start at the very beginning of this paradox. Take that same logic to a neutron star. This object can pack more mass than our sun into a ball small enough to fit inside a modest city's ring road, and yet it can spin 716 times per second that we've actually measured. One rotation every 1.4 milliseconds. On the equator of that star, a point on the surface is racing around at a significant fraction of the speed of light. You know the one rule your brain is screaming right now: that can't be stable. Because here's what nobody tells you. Simple physics, the kind you learn from watching a spinning pizza or a wobbling fan, says there should be a maximum safe spin rate. Spin too fast and the outward fling of rotation should overpower gravity, peel matter off the surface, and shred the whole object. We can even calculate a breakup limit. Go past a certain frequency, and gravity should lose its grip. And yet, astronomers keep finding neutron stars spinning right up against those theoretical edges. Some of them look like they're brushing the boundary. Some of them look like they're daring it. So what's going on here? How can a dead star spin so fast that its surface is moving at relativistic speeds and still remain intact? What kind of gravity, what kind of matter can survive that punishment without flying apart into a glowing cloud across space? By the end of this journey, we're going to pull apart that question. We'll see why these stellar corpses can spin faster than they seem like they should. What that reveals about nuclear matter packed beyond imagination. And how hidden rules of the cosmos quietly rewrite your everyday picture of motion and limits. Now let's begin. So let's zoom in on what too fast actually means here. We're talking about dead stars, the size of a city, spinning hundreds of times every second. Imagine taking something heavier than our sun and cramming it into a sphere barely 20 kilometers across, then hitting fast forward until one full rotation takes less time than a blink. Your everyday intuition says that should shred itself into a glowing cloud across space. Because here's what nobody tells you. Your sense of too fast comes from a world where gravity is weak and matter is soft. A playground merry-go-round makes kids dizzy at, a few turns per second. Push it faster and people slide off because the outward fling beats their grip and the friction under their feet. Now scale that picture up. A neutron star's equator can be whipping around at tens of thousands of kilometers per second, a decent fraction of the speed of light. On paper, the outward fling there should be absolutely brutal. So why doesn't the whole thing just explode? Why doesn't the surface peel off in rings, like some cosmic centrifuge gone wrong? This is where the paradox stops being a fun fact and starts poking at the foundations of physics. To even ask the question, You're testing how strong gravity can be when you crush a sun's worth of mass into a tiny volume, how rigid matter becomes at nuclear densities, and how space-time itself reacts when you drag it around in a furious spin. You know the one, that neat flat solar system diagram where planets trace calm orbits around a quiet star. Now replace the sun in that picture with a neutron star, spinning hundreds of times per second. Same gravity, yet, well, wildly different personality. Instead of gentle warmth, you get a lighthouse beam of radiation sweeping past you every millisecond, the heartbeat of a corpse refusing to slow down. It's the same universe, but the rules feel stretched. And yet something is above the planets. Something is below them. Out there, beyond our tidy orbital plane, are these invisible sirens of extreme physics, turning so fast that a point on their surface is racing at 1/10 the speed of light. And still they hold together. When you realize that, the phrase, "that's impossible," starts to sound less like a law and more like a lack of imagination. Because once you understand why these stars don't tear themselves apart, you're not just learning trivia, you're learning where the true speed limits of matter live, where gravity wins, and where rotation begins to cheat by warping the very fabric of space. And we're not done turning the dial yet. Next, we're going to see how some neutron stars get recycled and spun up, why there is a theoretical breakup speed, and what invisible brakes might be quietly slowing them down long before they ever reach it. So if you're still here, still picturing a dead star spinning so fast its surface is racing along at 1/10 the speed of light, that tells us something important about you. You're exactly the kind of person who's not scared off by extreme physics, who actually wants to see how far this can go before reality breaks. That's the kind of curiosity we make these deep dives for. Long form, carefully researched, slightly obsessive trips into the strangest corners of the universe take a lot of time to build, from tracking down obscure pulsar timing data to turning dense equations about gravity and angular momentum into a picture you can actually hold in your head. Because here's what nobody tells you. Videos like this only survive if the people who love them send a tiny signal back. So, if you're getting value from this, if you've already learned something new about how a star can die and still keep spinning like a cosmic buzzsaw, consider doing the simplest possible thing. Tap like. It sounds trivial, but that one click tells the algorithm there's an audience for long, nerdy conversations about neutron stars, not just 30-second clips. And if you want to keep going down this rabbit hole with us, hit subscribe. Turn on notifications if you're the type who wants to be there right when we drop the next episode on impossible orbits, broken symmetries, and places where space itself is dragged around by rotation. We're not going to spam you. We're going to show up with more of the exact kind of madness you're watching right now. If that doesn't feel right for you yet, that's fine. Keep watching. Let us earn it. Because the wild part is that we haven't even reached the most extreme end of the story. We've talked about fast. We have not talked about a stellar corpse spinning 716 times per second, or what it means for matter to be so close to its breakup limit that a tiny extra kick could, in principle, tear it apart. The really strange tricks are still ahead. Stars stealing spin from their companions, building up rotation the way a skater pulls in their arms, except that arms are whole streams of gas spiraling in from a binary partner. Invisible breaks in the form of magnetic fields and gravitational waves, quietly bleeding away angular momentum long before the star can truly test the ultimate speed limit. Now let's begin the next layer, To see why any of this makes sense, we first need a simple mental model of spinning objects that you already know. You know the one: an ice skater, a spinning chair, a collapsing cloud in the early solar system. So, let's start at the very beginning. Build that familiar picture, and then peel it apart until it can handle a city-sized star whirling hundreds of times a second. So let's cash in that familiar picture you've been carrying around since grade school. Not the exotic Neutron star yet. Your everyday textbook star. You know the one. It's a glowing, perfect circle on a white page. A yellow ball with soft rays coming out of it. If the artist is feeling ambitious, you get a few sunspots. Maybe a flare curling off to one side for drama. But the whole thing feels calm, like a lantern hanging in space, just there. If rotation shows up at all, it's a tiny curved arrow off to the side, almost an afterthought. One arrow, one label. Spins. That's it. The diagram doesn't pulse or blur or look dangerously fast. It just sits on the page, a static circle pretending to be a star. Because here's what nobody tells you. The way we draw stars quietly tells your brain that spin is optional. In that flat picture, the sun is less a raging fusion reactor and more a slow-turning porch light. You imagine it like a ball on a string that someone is lazily twirling, not whipping around hard enough to tear itself apart. Why would you suspect anything else? The page is silent. The orbit lines are neat. Gravity feels gentle. Nothing looks like it's in a hurry. Think about how the story usually goes. Star forms from a collapsing cloud. It lights up. It shines for billions of years. It ages. It swells. It dies in some spectacular way. Then we move on. Rotation gets one sentence, maybe. As it spins, and we're already talking about planets or solar flares or the life cycle chart taped to the classroom wall. So, let's start at the very beginning of your mental script. Star forms, shines, ages, dies. Clean, linear, almost peaceful. You're not wrong to have that picture. It works just fine if all you care about is where the solar system came from or why planets end up in a plane. But notice what's missing. Where is the sense that this calm lantern could ever turn into a city-sized object whirling hundreds of times a second? In most popular explanations, spin is treated like a side character. Nice detail, not the plot. We talk about mass, temperature, color, orbit, but not the raw, hungry, angular momentum hiding underneath. And yet something is above the planets. Something is below them, not in space, but in intensity. Ordinary stars are the training wheels version of rotation. This familiar model isn't exactly wrong, it's just dangerously gentle. It primes you to think, stars rotate, sure, but how wild can it really get? The answer is far beyond what that quiet yellow circle ever suggested. In the next section, we're going to take that lantern, crush it down to the size of a city, and watch the spin go from background detail to the main event. So let's slow down the violence for a second and go back to something you've actually seen. Not a star exploding. A skater. You know the one. Arms stretched out, spinning gently on the ice. Then, in one smooth motion, they pull their arms in and suddenly they're a blur. No rocket, no motor, no extra push. Just faster. Because here's what nobody tells you when you first see that. The universe is obsessed with keeping a particular kind of spin budget, the seam. Physicists call it conservation of angular momentum, but you already feel it in your body. When you're on a swivel chair and you tuck your legs in, you rotate quicker. When a kid on a playground pulls the chains of the swing inward while twisting, they whip around faster. Same spin budget, smaller radius, higher speed. The equation is fancy. The intuition is simple. Now let's begin to scale that intuition up. Take a huge, cold cloud of gas and dust in space. It's not perfectly still. It has a slow, lopsided swirl, like a lazy coin wobbling on a table. Gravity starts pulling that cloud inward. As it collapses, the spin can't just disappear, so the rotation speeds up. The more the cloud shrinks, the faster it turns. That's the solar system's origin story and the star's origin story at the same time. The collapsing cloud flattens into a disk, the central region, and gets denser and hotter, and the star ignites. So let's start at the very beginning of stellar rotation. Newborn stars inherit that original spin, just like planets inherit their orbits. The skater's arms are the giant cloud. The finished star is the skater pulled tight. You can picture it with a spinning pizza dough. Stretch it wide and thin, and it rotates lazily. Now imagine some invisible hand squeezing that same dough into a compact ball without letting it trade spin with anything else. It has to spin faster. Or think about a coin spinning on a table. As it tips and its spinning radius tightens, it races, then collapses. For a normal star like our Sun, this effect is noticeable, but it doesn't feel insane. The Sun rotates roughly once every 25 days at the equator. That's a huge ball of plasma, 100 Earths across, taking almost a month to turn around once. Slow, majestic, very lantern in the dark. But now, imagine we keep the Sun's mass and just keep shrinking the radius, the way we mentally shrink the skater's arms. Half the size, it spins faster. 1/10 the size, faster still. If you keep that angular momentum locked in while the radius drops to something city-sized, the required spin rate rockets into mind-bending territory. Rotations not every weeks or days, but fractions of a second. And yet, something is above the planets. Something is below them. Out in that same galaxy, there are stellar corpses that have actually done this, turning the gentle skater into a chainsaw. In the next section, we're going to meet them and ask why they can spin faster than they should and still hold together. So here's the quiet problem. The way we draw stars has been lying to you for years, without ever technically being wrong. Think about the classic star diagram you've seen 1,000 times. A perfect glowing circle, some arrows for nuclear fusion, maybe a little arrow curling around the outside that says rotation. You know the one. That tiny curved arrow in the corner is our first clue, because it tells your brain this is a side note. Rotation is treated like a footnote in the picture, not a headline. Because here's what nobody tells you. When you shrink an entire star's spin down to a single polite arrow, you're not just simplifying. You're editing your own intuition. You start to feel, deep down, that stars are mostly static, hanging there in space with a lazy turn that takes weeks or months. So when someone tells you a neutron star can spin hundreds of times per second, your first reaction is just, no, that can't be right. Not for something that used to be a sun. Imagine if we'd grown up with a different picture. Now, let's begin with a counterfactual. What if every textbook drew stars as obviously squashed, with their equators bulging out, almost like water balloons flung into a spin? What if the sun in your classroom poster had a fat, exaggerated waistline and a caption saying, "This is what rotation does"? You wouldn't think of spin as a background detail. You'd expect it to be dramatic, dangerous, central to how a star lives and dies. Instead, the diagrams are calm. The star is round. The little arrow is slow. So your brain quietly imports a hidden rule from everyday life. If something is spinning, there must be a sensible upper limit. a safe speed. A point where, like a toy on a string or a ride at the fair, gravity and material strength say, that's enough. Of course, a star can't spin like a blender, right? Here's the pattern interrupt. In the regimes we're about to visit, that everyday sense of too fast just breaks. When a massive star collapses into a ball only about 20 kilometers across, the same old gravity and the same old angular momentum combine into something your childhood diagrams never prepared you for. The polite arrow explodes into a blur. So, let's start at the very beginning of this reframe. The next time you see that flat, tidy star in a diagram, mentally grab it and spin it up until its equator bulges, until the picture looks wrong. Then remember, for neutron stars, reality is even more extreme. In the next section, we're going to follow that hidden spin through collapse and see why these stellar corpses can rotate faster than they should and still refuse to fly apart. So let's push that picture one step further. Don't just watch the neutron star spin from a safe distance. Step onto it. Imagine we press pause on reality. We turn off the lethal gravity, the ridiculous radiation, the way your atoms would be torn into a fine mist. For a moment, you can simply stand on the equator of a neutron star as if it were a solid, ordinary world. Now let's begin. Under your feet is a city-sized sphere, maybe 20 kilometers across, holding more mass than the sun. You know the one, a millisecond pulsar, one of the fastest we've ever found. It's rotating hundreds of times every second. That means the ground under you isn't just turning, it's racing. On the fastest pulsars, the equator whips around at a significant fraction of the speed of light. Not airplane fast, not rocket fast. A point on the surface can be moving at tens of thousands of kilometers per second. Blink, and the star has already spun around you several times. Try to look east, and the horizon is gone before your brain can finish the thought. Now compare that to every speed your body thinks it understands. The edge of a spinning carnival ride. You feel your stomach drop, but that's just a few meters per second. A bullet leaving a rifle, maybe a kilometer per second. A satellite in low Earth orbit, roughly 8 kilometers per second as it loops around the planet. Impressive, sure, but next to a neutron star's equator, all of that might as well be a lazy Sunday stroll. Because here's what nobody tells you. Your everyday intuition about spinning and flying off into space was built on those gentle speeds. On that carnival ride, you can feel yourself being pushed outward. On a muddy tire, droplets fling away in neat spirals. So if you're standing on a surface that's moving at 1/10 the speed of light, shouldn't you be launched into space instantly? Shouldn't the star's crust shred itself into a glowing ring, like a cosmic dog shaking off water? This is the paradox. The star is spinning too fast by every rule your body learned growing up on a slow, comfortable planet. And yet, it holds together. You don't fly off. The crust doesn't explode. The equator doesn't peel away and form a new mini-solar system in orbit around it. And yet something is above the planets. Something is below them. These dead stars sit out there in space, calmly defying your intuition about what rotation and gravity are allowed to do. To understand why they get away with it, we have to rewind, not just the spin, but the entire universe's clock, back to when this impossible object was a perfectly ordinary star. So, let's start at the very beginning. What happens when that star collapses and all its spin is squeezed into something the size of a city? Now, let's begin turning that collapse into a roadmap. We've raised the riddle. A dead star, crushed into a sphere the size of a city, spinning so fast that a point on its surface can be moving at 1/10 the speed of light. And yet, it doesn't fly apart. It just keeps going. For billions of years, how does that make sense? What is gravity really doing out there on the brink? Because here's what nobody tells you. Fast spinning star is a terrible mental picture. You know the one, the vague blur of a glowing ball whirling in empty space. By the end of tonight, we're going to replace that with a sharp, three-dimensional model in your head, where matter, gravity, and rotation are all locked in a very specific, very fragile negotiation. So, what's our path through this spin paradox? First, we rewind all the way. So let's start at the very beginning. How do you take an ordinary star and turn it into a neutron star in the first place? We'll follow a massive star from calm hydrogen burning to a collapsing core, to a supernova that blows off the outer layers and leaves behind a 20-kilometer remnant. Here, conservation of angular momentum is the main character. Shrink the radius by a factor of 100,000, and the spin has nowhere to go but faster. Then we'll ask, why stop there? If collapse alone can make a neutron star spin dozens of times per second, what pushes some of them into the ridiculous regime of hundreds of rotations per second? That's where accretion and recycling come in. We'll watch neutron stars in binary orbits siphon matter from a companion, stealing not just mass but angular momentum, like a cosmic figure skater being spun up by a partner who never gets tired. Next, we'll walk right up to the edge. What actually prevents these objects from spinning even faster? Why don't we see neutron stars whirling thousands of times per second until they shred themselves? Here we meet the real bouncers at the door, breakup limits where gravity can no longer hold on, superfluid interiors that move in quantized jumps, magnetic fields that act like invisible brakes, and gravitational waves quietly carrying energy away into space. Along the way, each piece adds a twist. Supernovae set the initial spin, superfluids redistribute it, magnetic fields channel it, and gravitational waves leak it. By the time we're done, too fast will have a precise meaning for you, grounded not in a flat diagram, but in the real physics of matter on the edge of collapse. So, what does that first moment of collapse actually look like from the star's point of view? From the star's point of view, that first moment of collapse doesn't start with a dramatic explosion. It starts in the quiet. Long before there's a neutron star, there's just a cold, dark cloud hanging in space. So, let's start at the very beginning. Picture a giant molecular cloud of hydrogen, helium, and a sprinkling of heavier elements drifting through the galaxy. It's not a neat ball. It's lumpy, turbulent, full of slow eddies and tiny motions. The whole thing is only a few degrees above absolute zero, so the gas barely stirs, but it does move. And hidden inside those motions is the seed of spin. Because here's what nobody tells you. Stars don't begin as still, perfect spheres. They begin as compromises between gravity pulling in and pressure pushing out. In one slightly denser patch of the cloud, gravity gets a tiny advantage, just a hair. That's all it takes. The gas there starts to contract. As it shrinks, those tiny initial swirls and drifts can't just vanish. Angular momentum has to go somewhere. You know the one, the classic figure skater analogy. Pull your arms in, you spin faster. Now scale that up to a region of space light years across, slowly drawing in on itself. As the cloud core collapses, any tiny initial rotation becomes more organized. Random motions average out into a preferred direction, a global spin. The result is not a flat disk yet, but you can already see a rotation axis emerging. At the center, a protostar forms, hot and dense and still growing. Around it, the collapsing cloud can't fall straight in along every direction because the gas carries angular momentum. Instead of dropping directly onto the core, it flattens into an accretion disk, orbiting in a rough plane. Gas spirals inward, like water circling a drain that can't quite swallow it all at once. Rotation is no longer an afterthought. It's the organizing principle. That spiral motion is what hands the newborn star its first real spin. As material in the disk loses energy and falls onto the protostar, it transfers angular momentum, giving the star a slow but definite rotation. Compared to a millisecond pulsar, this is leisurely. A few days, maybe a few weeks per turn. But the crucial point is that the star is already a rotating object carved out of a rotating cloud. Over the next millions of years, magnetic fields link the young star to its disk and to the surrounding space. Stellar winds blow charged particles outward. These processes act like a brake, bleeding the rotational energy away, spreading angular momentum into the wider environment. They can slow the surface, but they don't erase the spin entirely. They just redistribute it deeper inside and out into space. Why does that bookkeeping matter? Because when the core finally collapses in a supernova, all of that leftover angular momentum will be squeezed into a city-sized sphere. That's when modest rotation turns into something almost unimaginable. So if the bookkeeping matters, the next question is, which stars even get to play this game? Not every glowing ball in space is invited to the Neutron star after party. Most stars, including our sun, will never come close. Because here's what nobody tells you when you first learn the neat life cycle diagram. Only stars born with enough mass in the first place can die as neutron stars. You're looking at a very specific slice of the stellar population, roughly 8 to about 20 or 25 times the mass of the sun. Less than that, and gravity never gets strong enough to crush the core to nuclear densities. More than that, and the core can overshoot neutron star territory and collapse all the way to a black hole. So, let's start at the very beginning of that short, violent life. A massive star forms out of a collapsing cloud just like the sun did, but with far more fuel and far less chill. It roars through its hydrogen like a cosmic engine stuck at full throttle, fusing hydrogen into helium in only a few million years. That's a blink compared to the sun's comfortable 10 billion year schedule. Then the tempo ramps up. Once hydrogen in the core runs out, gravity squeezes the core. It heats up, and helium fusion kicks in. That stage is shorter. The core contracts again, lights up carbon, then neon, oxygen, silicon. Each new fuel burns hotter, faster, more desperately, like the star is sprinting up a ladder where every rung is on fire. By the time it's fusing silicon into iron, the clock isn't ticking in millions of years anymore. It's ticking in days. Through all of that, the angular momentum the star was born with never disappears. It just moves around. The bloated outer envelope can spin relatively slowly, dragged by winds, magnetic fields, and interaction with any nearby companion. Deep inside, the core can be rotating faster, decoupled from the surface by complex internal flows and magnetic torques. You can picture it as a spinning figure skater wearing a huge, flowing cloak. The cloak drags, but the body underneath keeps turning. Every time the core contracts between fusion stages, conservation of angular momentum quietly cranks the rotation rate up. Smaller radius, same angular momentum, higher spin. Even before the final catastrophe, the inner core of a massive star can be rotating several times per second, while the outer layers lumber along much more slowly. It doesn't look extreme yet, but the seeds are there. Now let's begin to connect that to neutron stars. When iron piles up and fusion can no longer pay gravity's bill, the core loses its last source of pressure support and collapses in a fraction of a second. That already spinning core is about to be shrunk from something Earth-sized to something city-sized. What happens to its spin when you crush it by a factor of 1,000 in radius? In the next section, we'll watch that collapse in slow motion and see how fast turns into absurd the moment the core crosses the neutron star line. So let's slow that chaos down, just for a moment, because once the core tips past that critical point, gravity doesn't negotiate, it wins. The trigger is surprisingly quiet, the buildup of iron in the core. You know, the one element that shows up at the end of all those fusion chains in massive stars. Iron is where fusion stops paying its own bills. Fuse lighter elements and you release energy, pressure, support. Try to fuse iron and you have to put energy in. Suddenly, the core has a growing iron heart that no longer helps hold the star up. Because here's what nobody tells you. The end of a massive star isn't when it runs out of fuel in some vague way. It's when the fuel it's making stops propping it up. Once enough iron piles up. Pressure from fusion stalls. But gravity is still there, still pulling. The balance tips. The core loses its main source of pressure support, and in a fraction of a second, it gives in. Now the collapse begins. Take something roughly Earth-sized, thousands of kilometers across, and let gravity crush it down to a ball only about 20 kilometers wide. That's like shrinking our entire planet into a city. How fast does that happen? Not over years, over milliseconds. The core doesn't gently contract. It implodes, free-falling under its own weight. And here's where rotation goes from noticeable to absurd. Angular momentum has to be conserved. It's the same rule that keeps the spinning skater speeding up when they pull in their arms. The collapsing core is doing that skater move on a cosmic scale. Shrink the radius by a factor of hundreds to thousands, and the spin rate has to skyrocket to keep the total angular momentum the same. If the original core rotated once every day or so, the newborn neutron star can be whipping around dozens, even hundreds of times per second. Inside that collapsing sphere, the physics gets brutal. Densities climb past nuclear density. Electrons are crushed into protons, forming neutrons and releasing a flood of neutrinos. The matter suddenly stiffens. The core hits a point where it can't compress much more. It slams to a halt and rebounds, sending a shock wave racing outward. That rebound, plus the neutrino blast, helps tear the outer layers of the star apart in the supernova you'd see from across the galaxy. And yet something is above the planets. Something is below them. Out in that three-dimensional galaxy, this tiny 20-kilometer sphere emerges from the explosion, already spinning like a cosmic engine, its surface moving at a significant fraction of light speed. Now let's begin to ask a sharper question. If it's born this fast, what stops it from spinning itself to pieces? To answer that, we have to zoom out and do something dangerous on YouTube. A little math. Not scary math. Just enough to see why a sun-sized core collapsing into a city-sized neutron star almost has no choice but to spin like a buzzsaw. So, let's start at the very beginning. Angular momentum. You know the one. The spin budget of the universe. It measures how much rotational motion you have, and it depends on three things at once. How much mass there is, how fast it's rotating, and how that mass is spread out around the spin axis. A skater pulling in their arms, a spinning pizza dough, a collapsing star, they're all playing with the same rulebook. In symbols, physicists write it as LIO. L is the angular momentum, I is the moment of inertia, and O is the spin rate. And here's the key. For a roughly spherical object, I scales like mR2. Same mass, smaller radius, much smaller I, because here's what nobody tells you in those neat textbook diagrams. The R2 part is brutal. Imagine the core of a massive star before it dies. It's thousands of kilometers across, rotating maybe once every few days. Slow, graceful, nothing like the frantic neutron star we ended with. Now let that core collapse until it's only about 10 kilometers in radius. That's a shrink factor of roughly 10,000 in size. Radius goes down by 104. The moment of inertia, which cares about R2, plunges by 108. Pattern interrupt. What happens if you keep the angular momentum the same while I drops by a factor of 100 million? The only thing that can respond is, whoa, the spin rate. It has to shoot up by the same factor. A core that lazily turned once every few days could in principle be whipped into spinning hundreds of times per second. A point on its surface would be racing around so fast that compared to your daily life in the solar system, it might as well be teleporting. Of course, real stars aren't perfect skaters. During the supernova, some angular momentum is dumped into the outer layers, into the expanding cloud of debris, into the asymmetric violence of the explosion itself. Gravity flings material out, magnetic fields twist, the picture gets messy. But the core doesn't have to keep all its original spin budget to become absurdly fast. Even a modest fraction of that theoretical 100 million-fold boost easily lands you in the realm of neutron stars rotating tens, hundreds of times per second. And that's before we add binary companions, accretion disks, and all the exotic tricks that can spin them up even further. Collapse alone, with nothing fancy, already gives you some of the fastest rotating objects in the universe. Which leaves us with the next puzzle. If basic physics is willing to crank them up so far, what finally slams on the brakes? So if collapse alone can wind these stellar corpses up, how do we actually see that spin from across the galaxy? We don't watch the star itself turning, we watch the lighthouse it carries. Now, let's begin with a word you've probably heard before, pulsar. You know the one. In the simplest picture, a pulsar is a neutron star with a magnetic field so intense it would erase every credit card on Earth from halfway to the moon, and that field is tilted relative to its spin axis. Charged particles race along those magnetic lines and create beams of radiation that shoot out from the magnetic poles. As the star rotates, those beams sweep through space like a cosmic searchlight. If one of those beams happens to cross our line of sight, every rotation sends a flash toward Earth. Pulse, pulse, pulse. Because here's what nobody tells you. We're not seeing the star blink on and off. We're watching a spinning beam skim past our tiny point in space, over and over, with nearly clock-like regularity. We first caught them in radio waves, where big dish antennas pick up those repeating blips. But pulsars don't care about staying in one part of the spectrum. Some fire in X-rays, some in gamma rays, some across multiple bands at once. Different telescopes, different detectors, same basic trick. Measure the time between pulses, and you've just measured the neutron star's rotation period. You're literally timing how fast a collapsed core is turning, from thousands of light years away. Some are leisurely by pulsar standards, spinning just a few times per second. Others tick tens of times per second, like a power drill that never runs out of battery. And then there are the true overachievers, millisecond pulsars. These are neutron stars rotating hundreds of times per second. Imagine something the size of a city, with more mass than the sun, completing a full turn in less time than it just took you to blink. The current champion is PSR J17482-6AD, buried in a dense cluster of stars. It spins 716 times every second. That's one rotation every 1.4 milliseconds. At the equator, a point on its surface is racing at a significant fraction of light speed, held together only by the brutal grip of gravity and the exotic matter inside. And here's where it gets even better. Those pulses are so precise, so stable, that we can track tiny changes in the spin. Slow drifts, sudden glitches, subtle wobbles. Each deviation is a clue about what's happening inside the star and what's tugging on it from the outside. In a sense, pulsars let us turn neutron stars into cosmic laboratories, which raises a sharper version of our puzzle. If we can see them spinning this fast, pulse by pulse, what hidden limits are they tiptoeing up against before they finally break? So here's the twist. For all that talk about neutron stars tiptoeing up against their limits, the very first thing we run into is a paradox in the opposite direction. If you take a massive star's core, a few times the mass of the sun, and you crush it down from something about the size of Earth's orbit to a sphere only about 20 kilometers across, conservation of angular momentum should go wild. Spin a figure skater, pull their arms in, you know the one. The smaller they get, the faster they twirl. Do that with a stellar core and simple back-of-the-envelope calculations say the newborn neutron star ought to spin hundreds, even thousands of times per second. It should be a blur, because here's what nobody tells you. When you run those naive collapse numbers, you get ridiculous answers. If the core kept all its angular momentum, a point on the surface could be moving at a decent fraction of the speed of light, skimming the edge of the breakup limit, where gravity is barely strong enough to hold the whole thing together. In that simple picture, too fast is the default. But then we actually look. We point radio telescopes at young supernova remnants and measure pulsars that are only a few hundred or a few thousand years old. The Crab pulsar, born in a supernova your distant ancestors saw in 10^4, spins about 30 times per second. That's fast by human standards, but it's nowhere near those extreme hundreds or thousands of rotations per second the toy model predicts. Many other young pulsars are even slower. So what happened to all that spin? Now, let's begin to complicate the picture. In a core collapse supernova, the outer layers don't politely sit there while the core shrinks. They explode outward. Those layers can carry away a huge chunk of the star's original angular momentum, like someone throwing pieces off a spinning merry-go-round. On top of that, intense magnetic fields threading the collapsing core can act like cosmic brake pads, coupling the core to the expanding envelope and draining rotational energy as the electromagnetic torques. And the collapse isn't clean. Some of that ejected material doesn't quite escape. It falls back, forming a swirling cloud and a brief accretion disk that can actually push against the newborn neutron star, transferring angular momentum in the wrong direction and slowing its spin. Gravity isn't just squeezing, it's negotiating. So from the very first moments, nature is both generous and strict with spin. It can create outrageous rotation, but it also deploys every trick it has to bleed angular momentum away. Which leaves us with a deeper question. if the universe is already slamming the brakes on newborn neutron stars, then how do some of them later end up spinning faster than any reasonable birth picture would allow? So here's the twist. For all the drama about insane spin rates, a neutron star's default setting is not infinite cosmic fidget spinner. It's brake pedal, pressed hard. Left to itself, a neutron star is designed to slow down. Now let's begin with the big one, magnetic braking. Take a ball of ultra-dense matter, squeeze it into a city-sized sphere, and give it a magnetic field 1 trillion times stronger than Earth's. Then spin it, fast. You've just built a gigantic electromagnetic brake. As the star rotates, its magnetic field whips through space, yanking on charged particles and launching beams of radiation. That whole process is stealing energy from the spin. Because here's what nobody tells you. A pulsar isn't just a lighthouse. It's a power plant that pays its electricity bill with rotational energy. Every radio pulse, every X-ray flash, every wind of electrons and positrons streaming away is quietly draining its angular momentum. The faster it spins, the more power it loses, and the harder that invisible brake bites down. Over thousands to millions of years, the rotation period stretches out from milliseconds to seconds, from blur to metronome. You can picture it like this. Imagine a figure skater spinning with arms pulled in. Then instead of opening their arms, invisible magnets in the air start grabbing at their hands, dragging energy out of the spin with every turn. The skater slows, not because they choose to, but because the environment refuses to let them stay that fast. Space does the same thing to neutron stars. And that's not the only thief. If a neutron star isn't perfectly smooth, if it has even a tiny mountain only a few millimeters high on its rigid crust, the whole object can wobble as it spins and radiate gravitational waves, ripples in space-time themselves. For very fast rotators, those waves can, in principle, siphon off angular momentum too. Harder to catch than radio pulses, but in the most extreme cases, they might be yet another hand on the brake. This isn't a theory we just like the look of. We can watch it happen. When astronomers time pulse years, they see their periods creeping longer with exquisite precision. A star that spins 10 times per second this year might spin 9.999 times per second next year. That tiny change, the spin down rate, is a direct measurement of energy leaking away into radiation, particle winds, maybe even gravitational waves. So, let's start at the very beginning of our expectations. An isolated neutron star should only ever slow down, never speed up, which means those ancient, ultra-fast millisecond pulsars are breaking the script. If the brakes are always on, then something out there must be leaning on the accelerator. Where does that extra angular momentum come from? The accelerator comes from somewhere very specific. It comes from a partner. Because here's what nobody tells you. A lot of the fastest neutron stars in the galaxy are not hot, young, freshly exploded corpses. They're ancient. Their magnetic fields have faded. Their original spin has long since been drained away by radiation and particle winds. By all rights, they should be slow, tired embers, and yet we see them ticking hundreds of times per second, like cosmic dentist drills. What happened? Now let's begin with a picture that doesn't look anything like our solar system diagrams. Take a neutron star, the dead core of a massive star, and put it in orbit around a perfectly normal companion, something like our sun. For a while, nothing dramatic happens. They just circle their common center of gravity, a quiet binary in the dark. But stars don't stay quiet forever. The companion evolves, swells, and turns into a red giant. Its outer layers puff up so far that the star can no longer hold them in a neat, spherical envelope. At that point, gravity cheats. Some of that bloated atmosphere spills past an invisible boundary and falls toward the neutron star. You might imagine it as a simple waterfall in space, gas just raining straight down onto the surface. But orbital motion refuses to be ignored. The infalling material keeps its angular momentum, so instead of plunging directly in, it spreads out into a thin, hot accretion disk, a kind of glowing, flattened ring wrapped around this 20-kilometer corpse. So, let's start at the very beginning of the spin-up story. That disk is the key. Every particle in the disk is orbiting faster than the neutron star itself. As friction and magnetic forces make the gas spiral inward, it has to get rid of angular momentum. Where does it go? Into the star. Each gram of matter that finally slams into the surface gives the neutron star a tiny push, a microscopic twist of the wrist. One push does nothing, but keep this going for millions, even billions of years. Those tiny nudges add up. A neutron star that was lumbering along at, say, 1 rotation every second can be wound up until it's spinning hundreds of times per second. That's when it becomes a millisecond pulsar, a recycled pulsar, blazing radio beams with metronomic precision. You know the one, PSR JWS74824446A, the record holder, whipping around 716 times per second. That's what a fully recycled neutron star looks like when nature has leaned on the accelerator for a very long time. And yet, something is above the planets. Something is below them. In the same way, something sits above and below our neat theoretical spin limits. Because this quiet, patient accretion process is how the universe takes old, slow neutron stars and shoves them right up against the edge of breakup. In the next part, we have to ask a harder question. Why don't they go over that edge and tear themselves apart? So if accretion is the shove, what does the cosmic hand actually look like? It's not a hose of gas spraying straight onto the neutron star. It's a disk, a thin, flattened whirlpool of hot plasma wrapped around the star's equator like a glowing vinyl record made of fire. Now let's begin with that picture. In this accretion disk, every ring of gas is in orbit, just like planets in a miniature solar system. The outer regions move more slowly, the inner regions whip around faster, and each ring carries angular momentum, a kind of rotational budget that gravity is constantly trying to spend. Because here's what nobody tells you. The disk isn't just a passive feeding tray. It's an engine for trading angular momentum. Gas in the disk doesn't fall straight in. It can't. To move inward, it has to get rid of some of its angular momentum, and it does that through friction, turbulence, and magnetic interactions that drag neighboring rings against each other. As the gas spirals inward, it drops deeper into the neutron star's gravity well, and to stay in orbit it has to speed up, just like a skater pulling their arms in. By the time it's skimming just above the surface, it's racing around at a significant fraction of the speed of light. What happens when that gas finally hits? It doesn't just splat and vanish. It shares its angular momentum with the star. You can imagine the disk as a stream of tiny rockets landing along the equator, one after another, all firing in the direction of rotation. Each one gives the neutron star the faintest nudge. Not impressive on its own. But keep that up for 1,000,000 years. 10 million. You know the one. The overnight success that took 1 billion tiny pushes. We've actually caught this process in the act. In X-ray binaries, where a neutron star siphons matter from a companion. we see bright X-ray emission from the hot inner disk and from the impact zones on the surface. In accreting millisecond X-ray pulsars, we can watch the pulses tick slightly faster as the system feeds the star. The timing changes are small, but they're real, and they tell us that the spin-up isn't just theory on a chalkboard. Over long time scales, the effect is brutal. A neutron star that started life rotating a few times per second can be spun up to hundreds of rotations per second. Some reach more than 600, closing in on the 716 rotation per second record holder. At those rates, a point on the equator is moving at a significant fraction of light speed, and the star is flirting with its theoretical breakup limit. So what stops the rockets from pushing it even faster? In the next section, we have to look at the hidden brakes built into space-time itself. Those hidden brakes only make sense if you first know what the speed limit sign actually says. Before we talk about slowing a neutron star down, we need to ask a simpler question. How fast could it spin if gravity was the only thing holding it together? So, let's start at the very beginning. For any object that's bound by gravity and rotating, there's a tug of war happening at the equator. Inward, you've got gravity trying to pull everything toward the center. Outward, you've got centrifugal acceleration, trying to fling material off into space. You know the one. That feeling in a fast car on a tight curve where your body wants to slide sideways. Same basic idea, just turned up to absurd levels. Because here's what nobody tells you. There is a hard limit where those two effects balance. At that point, the outward centrifugal acceleration equals the inward gravitational acceleration. We call the corresponding spin rate the breakup frequency. Cross that line, even slightly, and material at the equator is no longer truly bound. It doesn't politely stay on the surface. It starts to orbit, or just fly off. In simple Newtonian terms, the RE is almost embarrassingly clean. Gravitational acceleration at the surface goes like gm over r squared. Centrifugal acceleration goes like omega squared times r. Set them equal, gm r2, ratios O2r, solve for the angular velocity, and you get a rough maximum spin rate for a given mass and radius. No fancy relativity yet, just high school algebra wrapped around an object denser than an atomic nucleus. Now plug in some actual neutron star numbers. Take a fairly typical one, about 1.4 times the mass of the Sun squeezed into a radius of roughly 10 to 12 kilometers. Run that through the breakup formula and you get critical spin frequencies of around 1 to 1.5 kilohertz. That's 1 to 1,500 full rotations every second. At the equator, a point on the surface is racing around at a significant fraction of light speed, tracing a wild orbit only a few kilometers above the star's center. On paper, then, nature has given us a very clear-looking speed limit sign. Below about a kilohertz, gravity wins. Above that, centrifugal forces should start peeling the star apart. And yet something is above the planets. Something is below them. In neutron star terms, that above is the naive Newtonian picture, and below is the more complicated reality. Here's the paradox. Accretion from a companion can keep dumping angular momentum into a neutron star for millions or billions of years. So why don't we see any spinning at 1,200, 1,400, 1,500 times per second? What exactly slams on the brakes before they hit that breakup line? To answer that, we have to let space-time itself into the equation, and it doesn't play fair. So if space-time isn't playing fair, what does that actually look like on a real object? It looks like this: a dead star in a crowded star cluster, spinning 716 times every second, and somehow still holding together. This is PSR J174824446AD, You know the one, or at least you will now. It lives inside the globular cluster Tertian 5, a dense, ancient cloud of stars huddled together in the halo of our galaxy. In telescope images, Tertian 5 is just a fuzzy ball, but hidden in that blur is a neutron star rotating so fast that if you blink, it's already spun dozens of times. 716 rotations per second. That's its measured spin frequency. Translate that into something your brain can actually picture. One full rotation every 1.4 milliseconds. By the time a camera flash finishes, this thing has completed hundreds of turns. Because here's what nobody tells you. When you hear millisecond pulsar, you should be thinking precision industrial blender from hell, not a gentle lighthouse in space. Now, let's begin to feel what that means at the surface. Take a typical neutron star radius, say 15 to 20 kilometers. At 716 spins per second, a point on the equator is whipping around at roughly a tenth the speed of light. Not airline fast, not rocket fast, relativistic fast. A city-sized sphere where the equator is racing around at tens of thousands of kilometers per second, held in place only by gravity and the pressure of ultra-dense matter. On paper, that's still safe. Simple breakup calculations say many neutron stars shouldn't start tearing themselves apart until something like 1 to 1.5 kilohertz. So 716 Hz is technically below those naive limits. But here's the catch. Those limits depend on what's inside the star, on its exact mass and radius, and we don't get to open it up and check. Shift the equation of state, add a bit more mass, change the radius by a couple of kilometers, and suddenly 716 Hz does not look so comfortable. And yet something is above the planets. Something is below them. In the same way, PSR JAM 482446 AD sits right in that gray band between obviously stable and this should be throwing off chunks of itself into orbit. The disturbing part is that we see neutron stars spinning this fast, but not much faster. We see a whole population of millisecond pulsars clustering below about 750 Hz, as if nature is quietly telling us, that's far enough. So what is this? Are we already staring at the universe's speed limit for neutron stars, the fastest that matter can spin without shredding under its own gravity? Or are there even more extreme pulsars hiding in the galactic plane, too faint or too oddly aligned for us to catch, waiting to force us to redraw our breakup lines and rewrite our models of dense matter? Because once you ask that, you have to consider that the breaking might not come from the surface at all, but from something leaking straight out of space-time itself. So if the breaking might not come from the surface, we have to go where the real action is. Inside. Because here's what nobody tells you. The part of a neutron star you can picture, that glowing sphere sweeping through space, is basically just the shell. Now let's begin with the simplest mental X-ray we can manage. On the outside, there's a whisper-thin atmosphere, centimeters to meters thick, a haze of electrons and light nuclei caged by ridiculous gravity. Beneath that, a solid crust, a lattice of atomic nuclei in a sea of electrons, like an ultra-compressed metal stretched across a 20-kilometer ball. It sounds familiar enough, like an extreme version of the planets you know from those flat solar system diagrams. But keep sinking. The nuclei get squeezed so hard that electrons are rammed into protons, making neutrons faster than you can say periodic table. Very quickly, you're in a region where the density beats the nuclei inside ordinary atoms. At that point, the old picture of matter just breaks. You don't have atoms in orbit around anything. You have a quantum ocean of mostly neutrons, with a sprinkling of protons and electrons threading through it. And yet, Something is above the planets. Something is below them. Because this isn't just dense, it's weird. At those pressures and temperatures, neutrons are expected to pair up and form a superfluid, while the remaining protons become a superconducting fluid. That means the interior of a neutron star behaves like a gigantic, macroscopic quantum state, not in a lab flask, in a mountain mass chunk of matter spinning hundreds of times per second. Here's the pattern interrupt. You think of spin as smooth like a spinning globe, but a superfluid can't rotate that way. It has to store angular momentum in discrete, quantized vortices, tiny tornado lines threading the interior. As a star is torqued by accretion or slowed by magnetic drag, those vortices move, pin, unpin, and jump. The superfluid can temporarily hoard angular momentum and then dump it into the crust, making the whole star suddenly spin faster and glitches. So when you ask, how fast can this thing orbit its own axis before breaking? The answer partly lives in how those quantum whirlpools rearrange themselves. Go deeper still, and the picture gets even stranger. Some theories say that at the very highest densities, the neutrons themselves melt into deconfined quark matter, or form exotic phases like color superconducting quark soups. Change the interior recipe like that, and you change how stiff the star is, how compressible it is, how much pressure you get for a given density. That is the real lever on the spin limit. The equation of state of this ultra-dense matter, how pressure responds to squeezing, decides how compact the star can be, how strong its self-gravity is, and whether the surface is far enough inside the grip of gravity to survive a 700 Hz spin without flying apart. Different interiors mean different breakup speeds, so the mystery of faster than they should isn't just about rotation. It's about what kind of impossible matter you're willing to allow at the core. In the next part, we'll see how astronomers try to read that hidden equation of state from a handful of spinning dots and a rain of very quiet, very distant pulses. So, we've got this hidden equation of state written in nuclear handwriting, and we're trying to read it from a few spinning dots. But every so often, one of those dots does something rude. It jumps. Astronomers call it a glitch. You're watching a pulsar that's been slowing down with clock-like regularity, its pulse period stretching by trillionths of a second per day, and then in a single observation, the pulses arrive just a little too early. The rotation rate has suddenly increased. Not by much on human terms, but by a lot for a dead star that weighs more than the sun. Because here's what nobody tells you. These glitches are not tiny numerical errors. They're real, abrupt spin-ups, sometimes parts in a million, happening in objects 20 kilometers across, with gravity so strong a teaspoon of their matter would outweigh a mountain. The Vela pulsar is the poster child. You know the one. Every few years it jerks faster, like a cosmic record that skips forward a groove. So what could possibly grab a neutron star and twist it? Not some passing cloud in space. The culprit seems to be inside. The outer few percent of the star is a solid crust, an ultra-dense nuclear lattice. Beneath that, physics gets even stranger. A superfluid interior, where neutrons flow with zero viscosity and rotation is carried not by a smooth whirl, but by countless microscopic vortices, each one a tiny quantum whirlpool. Those vortices don't just drift around freely, they can pin to the crust. Over time, as the crust spins down due to magnetic braking, the pinned superfluid tries to keep its faster rotation. Tension builds between the two, like a flywheel locked to a slowly braking wheel. And then, at some critical point, A whole forest of vortices suddenly unpins and moves outward, dumping angular momentum into the crust in a single, quantized shove. The result is the glitch you see in the pulses. A dead star, jolting faster in an instant. Now let's begin to appreciate what that means. A neutron star isn't a simple rigid ball. It's a layered, dynamic system, where different components can hoard and trade angular momentum in discrete jumps. In the same way the solar system isn't really flat, this single number we call the spin rate hides a three-dimensional drama under the surface. And yet, something is above the planets. Something is below them. Inside neutron stars, something is above and below the crust too. Superfluid regions storing rotational energy, then releasing it in glitches. Repeated glitches in Vela, in the Crab pulsar, and in dozens of others have let us sketch a picture of how thick the crust must be, how strongly vortices pin, how quantum this bulk matter really is. But if the interior can store and suddenly unload spin, what else can it do? Could the same hidden machinery that makes glitches also decide the ultimate speed limit for a neutron star's rotation? In the next part, we'll push that question to the breaking point. So if the interior can hoard angular momentum and then dump it in a glitch, what is all that spin doing to the outside? Because here's what nobody tells you. Once a neutron star is rotating hundreds of times per second, you can stop picturing a neat little sphere. It's not a billiard ball. It's more like a cosmic water balloon being whipped around by gravity. Now, let's begin with a picture you already know. Take a spinning pizza dough, or the Earth itself. When something rotates, it bulges at the equator and flattens at the poles. Gravity is trying to pull everything toward the center, but rotation throws material outward along the equator. So the shape settles into what physicists call an oblate spheroid. You know the one, wider around the middle, slightly squashed top and bottom. For a neutron star, that slightly goes out the window. If it's spinning hundreds of times per second, the equator is racing around at a significant fraction of the speed of light. The result is a star that is measurably flattened, with an equatorial radius noticeably larger than its polar radius. That distorted shape means the balance of forces at the surface is different at the equator than at the poles. At the poles, gravity wins easily. At the equator, it's a knife-edge competition between gravity pulling in and centrifugal effects pushing out. As the spin cranks up, that equatorial bulge grows. The surface there is effectively climbing uphill in the star's gravity field, making it easier for material to drift outward. Long before you hit the dramatic textbook breakup speed, you can reach a quieter but still dramatic regime: mass shedding. Little by little, material at the equator can start to escape, forming a tenuous ring or feeding a surrounding cloud of debris. The star doesn't explode, it just leaks. But that leak robs it of angular momentum. How do you keep spinning faster if every extra push throws more of you off into space? And there's another twist hiding in that not quite spherical shape. If the mass distribution isn't perfectly symmetric, if the bulge is lumpy or the crust is slightly warped, then as the star rotates, it can radiate continuous gravitational waves. Tiny ripples in space-time, streaming away with every turn, carrying off angular momentum. It's like a braking system you can't switch off. So, let's start at the very beginning of the speed limit story. The more a neutron star deforms, the more escape routes it opens for its spin. Mass shedding, gravitational waves, magnetic torques, all of them feed on that equatorial bulge. And yet, something is above the planets. something is below them. In the same way, something above and below the star's ideal spherical shape might be quietly enforcing a maximum rotation. But are those breaks strong enough to explain why we never see spins past about 1,000 times per second? That's where the next layer of physics comes in. Those breaks are strong, but they're not made of metal. They're made of magnetism. Now let's begin with a reminder that sounds almost fake. Neutron stars don't just have magnetic fields. They have magnetic fields trillions of times stronger than Earth's. You know the one on your fridge? Multiply that by a number so ridiculous it stops feeling real, and you're still not close. These are some of the most magnetized objects in the universe, and that magnetic field is welded to the star's rotation. As the star spins, those magnetic field lines don't just sit there in space like a flat diagram. They sweep around, cutting through the surrounding plasma, dragging charged particles with them. The result is a magnetosphere, a rotating electromagnetic bubble that reaches far beyond the solid surface. And that bubble doesn't just glow, it radiates away energy, like a cosmic dynamo constantly bleeding power into space. Because here's what nobody tells you. A spinning magnetic field is not just a pretty picture for a textbook. It exerts torque. The rotating field launches beams of radio waves, X-rays and gamma rays, and it flings out winds of relativistic particles. All of that comes at a cost. The energy has to come from somewhere, and gravity isn't paying the bill. The rotational energy of the neutron star is. So the magnetosphere acts like a brake pad pressed against the star's spin, steadily extracting both energy and angular momentums. We see this most clearly in young, highly magnetized pulsars. The Crab pulsar, born in a supernova, not that long ago in cosmic terms, is spinning about 30 times per second and slowing down. We can measure its period increasing, millisecond by millisecond, as magnetic braking drains its rotational reservoir. Imagine a figure skater with a gigantic invisible parachute attached. How fast could they really spin up before the drag wins? In accreting systems, the picture gets even trickier. The neutron star is trying to steal angular momentum from an accretion disk, using gravity to spin itself up. But that same magnetic field can reach out and grab the disk, truncating it before it reaches the surface and channeling matter along field lines onto the magnetic poles. Depending on where the disk is truncated, inside or outside the corotation radius, the field can either act like a conveyor belt that spins the star faster, or like a magnetic propeller that actually flings material away and breaks the rotation. So, let's start at the very beginning of the real paradox. Strong magnetic braking means that only neutron stars with weaker or decayed fields can be pushed to those ultra-fast, hundreds of rotations per second rates. That's why the most extreme millisecond pulsars tend to be old, recycled, and magnetically worn down. And yet, something is above the planets. Something is below them. In the same way, something beyond magnetism still seems to be limiting the very fastest spins. If magnetic brakes aren't the whole story, what other invisible hands are gripping these stars? One of those invisible hands doesn't grab the star at all. It pulls on space itself. Because here's what nobody tells you. Once a neutron star is spinning fast enough, it can literally leak rotation into the fabric of the universe as ripples. You've heard of these ripples. Gravitational waves. You know the one. The Nobel Prize headlines about black holes crashing together, about neutron stars spiraling in and ringing space like a bell. Those detections were all about violent collisions, brief flashes in the dark, two massive bodies in a tight orbit, accelerating like crazy, shaking the gravitational field so hard that the waves crossed hundreds of millions of light years and still nudged LIGO's mirrors by less than the width of a proton. But here's the twist. You don't actually need a collision. You just need something massive, spinning, and not quite perfectly symmetric. A completely smooth, perfectly round neutron star rotating steadily is like a perfectly balanced wheel. It won't send out continuous gravitational waves. In principle, it could sit there, whirling hundreds of times per second, and space would stay quiet. Real neutron stars are not that polite. Their crusts can crack. Magnetic fields can drag material around. You can get tiny mountains, only a few millimeters high, frozen into a surface under more gravity than the entire solar system can muster. Or the whole star can wobble slightly, like a spinning top that's just a touch off-center. That tiny asymmetry means the mass distribution is lopsided, and a lopsided mass distribution sweeping around hundreds of times a second is exactly what gravitational waves love. So now the star is not just shining in radio or X-rays, it's humming in gravity. Those waves carry away energy and angular momentum, bleeding rotational power directly into space. The faster the spin, the stronger this effect can become. At very high frequencies, gravitational radiation stops being a quiet background and starts to look like a serious drain, a hidden tax on absurdly fast rotation. Now let's begin to connect this to observations. LIGO, Virgo, and their cousins aren't just listening for spectacular mergers. They're also running long, patient searches for continuous gravitational waves from known pulsars, taking that flat timing picture we see in radio and asking, is there a matching ripple in space? So far, they've heard silence. But that silence is loud in its own way because it tells us those neutron stars can't be too deformed. Their mountains must be incredibly small, or the interior wobble must be damped. And yet something is above the planets. Something is below them. In the same way, there might be a spin threshold above which this gravitational hum suddenly switches on, an invisible leak that kicks in and refuses to let the rotation climb any higher. If that's true, then the ultimate speed limit isn't just about matter tearing apart. It's about space-time itself pushing back. But gravitational waves are only one suspect. Inside the star, something even stranger is waiting. Inside that star, all those braking mechanisms we've been hinting at start to team up. And when they do, something subtle but powerful happens. The universe quietly refuses to give us a 2,000 Hz pulsar. So, let's start at the very beginning of this puzzle. On paper, a typical neutron star, 1.5 times the mass of the Sun and about 20 kilometers across, can spin absurdly fast before it breaks apart. Simple breakup calculations say you can push it up to around 1 to 1.5 kilohertz. A full rotation every millisecond or so before gravity loses its grip and material at the equator starts to escape. You'd expect to see at least a few daredevils up there, right? And yet, the fastest pulsar we've ever found sits at 716 Hz, and the population drops off sharply above about 600. Because here's what nobody tells you. The limit isn't a single hard cliff. It's a swamp of competing processes that all get nastier as the spin rate climbs. Magnetic braking, for one, is like an invisible hand on the flywheel. The star's magnetic field drags against the surrounding plasma in space, flinging energy and angular momentum away. Double the spin, and the power you lose to that magnetic wind ramps up dramatically. Layer on gravitational waves. If the star isn't perfectly smooth, Each rotation sends out ripples in space-time, and the faster it spins, the more energy those ripples steal. Then add mass shedding at the equator once you're close to breakup, where the surface is trying to orbit faster than gravity wants to allow. None of these is fatal on its own. Together, they create a soft ceiling, a region where pushing faster gets exponentially harder. Now bring in accretion. In a binary system, a neutron star feeds from a companion, building a hot, bright accretion disk that looks, in miniature, like a tiny, furious version of the flat solar system diagrams you've seen. Infalling matter spirals in, transfers angular momentum, and spins the star up. But as the spin climbs, those magnetic torques, gravitational waves, and near breakup effects push back harder and harder. At some point, spin up and spin down balance. You hit an equilibrium frequency. Not the theoretical breakup rate, but a safer, enforced cruising speed below it. Could we simply be missing the true speed demons? You know the one. The argument that selection effects are always to blame. Ultra-fast pulsars might be more short-lived, or beam their radio waves in narrower cones that miss Earth, or bury their pulses in messy accretion noise. And yet, something is above the planets. Something is below them. Our surveys are now sensitive enough that the near total absence of pulsars above by 700 Hz is telling us this isn't just a detection trick, which nature seems to have drawn a practical line well below the wildest theoretical maximum, which is why 716 Hz feels like brushing the edge of what's allowed. But if the universe is enforcing a speed limit, what exactly inside a neutron star is acting as the cosmic traffic cop? So when we say these stars are spinning faster than they should, we have to stop and ask a slightly awkward question. Faster than they should according to whom? Because here's what nobody tells you. That shocked tone you hear in headlines is usually reacting to a very particular version of physics. The neat, chalkboard version, not the full, messy, astrophysical reality. In the clean picture, you draw a sphere. You balance gravity pulling in against centrifugal force pulling out. You plug in a simple density and you get a breakup frequency. Maybe a few hundred hertz. Anything above that looks illegal. But that's like judging the whole solar system from one flat diagram. You know the one. The tidy row of planets on a single line, as if nothing ever strays above or below the ecliptic plane. The moment you zoom out into real three-dimensional space, that picture breaks. Early neutron star spin limits were that flat diagram. Elegant, intuitive, and deeply incomplete. Those first estimates treated a neutron star as a uniform, rigid ball of nuclear matter with a very simple equation of state. And they quietly ignored some of the ways angular momentum can be lost. No strong internal magnetic fields twisting the interior. No superfluid layers slipping past each other. No gravitational waves sneaking energy away. In that stripped down world, you get conservative limits, and 716 Hz feels outrageous. Now let's begin to upgrade the model. Over the last few decades, nuclear physicists have built far more realistic equations of state for ultra-dense matter. And simulators have let entire rotating stars live inside their computers. When you let the interior stratify, when you allow matter to be more compressible in some layers than others, the star can actually spin faster before gravity loses its grip. The theoretical ceiling moves up, sometimes close to or even above a kilohertz. At the same time, our picture of how these stars are spun up has changed. Accretion isn't just a gentle drizzle, it's a complex magnetized flow that can either break or boost the orbit of the star depending on how the magnetic field threads the inner disk. Fold that into the simulations, and the range of allowed spin rates stretches, inching toward what we actually observe. So the real paradox isn't that neutron stars spin faster than they should. It's that they spin just fast enough to back us into a corner and force us to refine our theories of matter and gravity at densities we can't reproduce on Earth. They're not rule breakers, they're stress tests. And yet something is above the planets. Something is below them. In the same way, neutron stars sit above and below our simple models, showing us exactly where the flat picture bends. The question isn't, how are they allowed to spin so fast? It's, what hidden physics is quietly enforcing the limit we see? Hold on to that, because next we're going to follow the energy and see which mechanisms are actually doing the enforcing. So if gravity is doing the enforcing, what rules is it actually following inside that star? This is where we hit one of the biggest blank spots on our cosmic map, the equation of state of ultra-dense matter. Now let's begin with what that phrase really means, because it sounds more intimidating than it is. An equation of state is just a rulebook that tells you how pressure responds when you squeeze a material, how pressure and density are linked. For a gas in your room, we have simple equations. For the plasma in the sun, we have pretty good ones. But for matter crammed to and beyond a nuclear density, like inside a neutron star, that rulebook is contested. Because here's what nobody tells you. Almost everything about a neutron star's maximum spin is hiding inside that one relationship between pressure and density. Change the rulebook, and you change how big the star is, how massive it can be, and how close it can skate to break up before gravity loses its grip. Imagine one extreme, a stiff equation of state. In that picture, as you compress the matter, the pressure shoots up quickly. The star pushes back hard against gravity. That gives you a neutron star that can support more mass and puff out to a slightly larger radius, still only around 20 kilometers. But on the bigger side of the scale, a larger, more strongly supported star can sometimes spin faster without flying apart, because gravity and pressure together are better at holding the equator down as it tries to fling off into space. Now flip it. A soft equation of state means the pressure doesn't rise as fast when you squeeze. Gravity wins more easily. The same mass collapses into a more compact star, with a smaller radius and a tighter grip from its own gravity. That sounds like it should help, right? Smaller object, stronger gravity, easier to hold together at high spin. The twist is that the detailed balance between mass, radius, and internal pressure can make these soft models hit their breakup limit at lower spin frequencies. In that case, the star reaches its too fast point sooner. So, let's start at the very beginning of how we test these pictures. We go out and measure real spins, the fastest millisecond pulsars we see, some ticking hundreds of times per second, become speed traps for theory. If a particular equation of state says no neutron star can safely spin above 500 times per second, and we calmly observe one doing 600, that rulebook is out. Gone. And yet something is above the planets, something is below them. In the same way, each millisecond pulsar sits above and below different theoretical curves on a graph of mass, radius, and spin. When we combine spin rates with mass and radius estimates from X-ray observations and gravitational wave events, we start crossing out huge swaths of possible equations of state. Every fast pulsar becomes a tiny laboratory for nuclear physics, probing densities we can't reproduce on Earth. In the next section, we'll push even deeper inside and ask what exotic phases of matter those equations might be hiding. So once you have those spin rates and those dense matter equations fighting it out on paper, a darker question shows up. What happens if a neutron star doesn't stop where the math wants it to, and accretion just keeps pushing? Now let's begin with the brutal reality of a star being force-fed. In a tight binary, a neutron star can siphon gas from its companion, building an accretion disk that whirls around it like a tiny, murderous version of the solar system. Every bit of matter that spirals in brings angular momentum, spinning the star up. At first, this is gentle recycling, but as the spin approaches the breakup frequency, the crust and interior are no longer relaxed passengers. They're being pulled toward the limit where gravity and centrifugal force are in a dead heat. Because here's what nobody tells you. The crust of a neutron star can crack. As the spin rate climbs, the solid outer layers are stressed by the changing shape of the star, trying to bulge at the equator and flatten at the poles. Deep inside, superfluid neutrons and superconducting protons have to rearrange their flow patterns. You're no longer just spinning a ball. You're driving a nuclear lattice and quantum fluids into regimes where tiny asymmetries can explode into full-blown instabilities. One of the strangest is the R-mode instability. Imagine the fluid interior sloshing in patterns that ride along with the rotation, like waves sliding over the surface of a spinning cloud. At very high spin, those waves can grow instead of dying away, and they radiate gravitational waves that carry off angular momentum. It's like the star discovers a hidden exhaust vent. The faster it spins, the stronger the gravitational wave braking gets. Push it too hard with accretion, and R modes can light up, dumping spin faster than the disk can add it. But what if you keep feeding it mass as well as spin? There's a second cliff edge. Every equation of state predicts a maximum mass, above which no pressure in the universe can hold the star up against its own gravity. Cross that line, and the neutron star collapses into a black hole. No fireworks on the surface, no dramatic tear-off of the equator. From the outside, the pulse train could just cut off, mid-beat. The spin story ends not in shreds, but in silence. Astronomers looking at accreting millisecond X-ray pulsars see hints of these balancing acts. We see many systems spun up to a few hundred hertz, but almost none beyond about 700. It's as if there's a soft ceiling where spin-up stalls. Is it R modes? Magnetic torques? Subtle changes in the star's shape that enhance gravitational wave emission? You know the one. The universe loves to hide its regulators inside the extremes. And here's the pattern interrupt. We went in asking, why don't they just break apart? But as these stars approach the edge, the rules themselves seem to bend. New channels open to bleed off spin and mass long before the crust can truly fly apart. They don't get to break the rules, because at those extremes, the rules rewrite them. In the next section, we'll follow that rewrite inward, into the exotic phases of matter that make these self-defense mechanisms possible in the first place. So if the rules are rewriting the star, there's an obvious question hanging over all of this. Are they rewriting it so hard that a 1,000 hertz neutron star simply can't exist? Or have we just not caught one in the act yet? Right now, 716 hertz is the champion. You know the one, PSR J1748-2446 AD, spinning once every 1.4 milliseconds. For almost 2 decades, it's just sat there at the top of the leaderboard, daring us to find something faster. Is that because nature really slams on the brakes around that frequency? Or because our telescopes, our algorithms, and our expectations are all tuned to the wrong picture of what an ultra-fast pulsar would look like? Because here's what nobody tells you. The way we detect most pulsars quietly builds in selection effects. We look for clock-like radio pulses sweeping across Earth. A lighthouse beam that happens to cross our line of sight. Spin a neutron star faster and you don't just get more flashes per second. The magnetic field can pinch the beam into a thinner cone. The emission can migrate to higher energies. And relativistic effects can smear or distort the pulses. At some point, the beam might be so narrow or so misaligned with us that the solar system never sits in its path. Faster rotation also means harsher self-defense. Near a kilohertz, the equator is racing at a good fraction of light speed. The star bulges, gravity weakens sideways, and any extra push from accretion can fling matter off into space. If gravitational waves are draining angular momentum, or if the interior superfluid is coupling more efficiently, a would-be 1000 Hz pulsar might streak past that speed limit for only a brief moment before spinning down. Short-lived, rare, narrowly beamed, that's a recipe for hiding from us. But suppose we do catch one. A neutron star ticking at 1000 Hz or above would be a direct challenge to our current equations of state for ultra-dense matter. It would say very clearly that the interior can support higher spin and stronger centrifugal flattening than most models allow. Suddenly, the detailed balance between magnetic braking, accretion torques, and gravitational wave losses would be wrong. We'd have to redraw the breakup line, rethink how superfluids move inside the core, and revisit whether exotic phases like hyperons or quark matter are really softening the star, or if something stiffer is hiding there. Now let's begin to look for it. New radio surveys with wide field arrays are scanning the sky faster and deeper than ever. X-ray missions are catching millisecond flickers from accreting neutron stars in corroded stellar clusters. And in the background, gravitational wave detectors are quietly listening for continuous, razor-steady tones from asymmetric, ultra-fast rotators we might never see in light at all. Somewhere in that data, could there be a heartbeat at 1,000 ticks per second, right on the edge of breakup? If we find it, that single spinning corpse might become the most important clock in the universe. And in the next section, we'll finally open it up and see what its ticking heart is really made of. So let's finally cash in that promise. We've been treating a millisecond pulsar as this abstract ticking heart. But what if you flew right up to one? What if, instead of listening from across the galaxy, you tried to land on a dead star spinning hundreds of times per second? Now let's begin with the approach. You're in a ship, dropping out of warp a few thousand kilometers away. The pulsar is tiny in your window, only about 20 kilometers across, but it dominates the picture. Twin beams of radiation sweep past like lighthouse beams on fast forward. As you close in, the surface stops looking like a solid crust and starts to blur into a glowing band, because points on the equator are whipping around at 1/10 speed of light. Your brain wants to call it a ring. Your instruments insist it's a sphere, because here's what nobody tells you. From a safe distance, it's easy to think of gravity and rotation as equal players, like orbit and spin in a neat solar system diagram. Up close, that illusion dies fast. As you drop toward the surface, the ship's artificial gravity might be set to 1g. The neutron star is about to hit you with something like 100 billion g. You don't step out of the airlock. You are ripped out, stretched, and crushed by tidal forces long before you ever touch the crust. Those tides are brutal. Your feet feel more gravity than your head, by a factor that would tear molecules apart. And yet, something is above the planets. Something is below them. On this world, up and down are so violently defined by gravity that the idea of floating is gone. Even at the equator, where the centrifugal effect from that insane spin is strongest, the outward push is just a rounding error. You can imagine pausing the rotation for a moment, freezing the star in space. That surface gravity is your baseline. Now spin it back up to 700, 800 rotations per second. At the equator, the effect of gravity drops a bit. The way you weigh slightly less at Earth's equator than at the poles. On a neutron star, that difference might be 10–20%. Noticeable in the equations, completely irrelevant to your survival. So if you could somehow survive the radiation, the heat, the tidal shredding, and stand there, you wouldn't be flung off. You'd be pinned down with a force that makes mountains behave like liquid. At the poles, where rotation barely helps you, you're pressed even harder into the crust. At the equator, you get the gentler version of doom. And that's the point. Even spinning too fast, brushing the edge of breakup, the star holds itself together, and it holds you down. Its density makes rotation look weak. In the next section, we'll peel back that crust and ask what kind of matter can laugh in the face of gravity this extreme and still not fly apart. But there's one more way the star holds you down. That's even stranger than nuclear matter. It cheats by messing with time itself. Up to now, we've treated this thing like a ridiculous but still familiar spinning ball. Gravity pulls in. Centrifugal effects push out. The crust and the super-dense interior keep the whole picture from flying apart. That's the Newtonian version. It's useful. It's also incomplete. Because here's what nobody tells you. When you spin a mountain of mass this fast, you don't just move through space. You drag space along with you. This is where general relativity walks in, looks around, and quietly rearranges the furniture. A rotating neutron star doesn't just sit in a pre-existing arena of space and time. It twists that arena. The name for this is frame dragging. Close to the star, the reference plane of the universe itself is being tugged in the direction of the spin, as if the vacuum were a very stiff, very reluctant fluid being stirred by a cosmic spoon. So if you tried to hover near the equator, you wouldn't just be fighting gravity and rotation. You'd also be fighting the fact that local space is already being carried along. In a sense, standing still above the surface means you have to orbit backwards through a current of space-time that's trying to sweep you around. Light has to play this game too. Beams sent in the direction of the spin take slightly different paths and times than beams sent against it. Time on the spinning corpse does not tick the same way in every direction. And yet, something is above the planets. Something is below them. We use that flat ecliptic plane in the solar system as our mental zero. Near a neutron star, there is no simple plane. The orbits in the accretion disk feel the warped geometry. Their inner edges precess, wobble, and slowly twist like a tilted ring of gas trying to decide which way around even is. That twisting doesn't stop at the matter. The magnetosphere, those huge magnetic field lines that guide charged particles, gets dragged too. The lighthouse beams of pulsars sweep past us, not just because the star spins, but because the underlying space it's embedded in is slightly twisted. When we time those pulses to microsecond precision, frame dragging and other relativistic corrections quietly sneak into the equations. Ignore them, and your model of the maximum spin rate will be just wrong enough to embarrass you. These effects don't rip up the basic breakup limit. They nudge it. They shift the exact frequency where gravity, rotation, and nuclear forces balance on a knife edge. Neutron stars spinning near their limits become laboratories where gravity, quantum physics, and relativity all collide in one compact experiment. Now, let's begin to peel back that experiment. If relativity is twisting space around the star, what exotic phases of matter are twisting inside it, holding the whole machine together while it races the clock? Those exotic phases of matter are also where your intuition quietly breaks. Because here's what nobody tells you. Your entire sense of what spinning too fast means was trained on the weakest, fluffiest objects in the universe. Think about the things you've actually seen rotate. Bicycle wheels, fidget toys, potter's wheels. Maybe, if you're lucky, a slow-motion video of a collapsing bridge or a rocket stage tumbling in space. All of those live in a world where material strength is the bottleneck. Spin a car tire too fast and it rips apart long before gravity matters. Even with planets in the solar system, it's still mostly about rock and ice holding themselves together, not gravity playing nuclear-scale tug-of-war. Neutron stars flip that picture inside out. Here, gravity is so overwhelming that it is the structure. The material is so dense that a teaspoon would outweigh a mountain, and the forces between neutrons are orders of magnitude beyond what you've ever asked steel or stone to endure. The usual failure modes your gut expects: cracks, chunks flying off, things bending and snapping, still exist, but they play out in a regime where space, time, and nuclear physics all get a vote. So when you hear that a neutron star can spin hundreds of times per second, with its equator whipping around at a decent fraction of light speed, your brain tries to paste that onto a mental image of a spinning ball or a planet. It feels wrong. It feels like it should fly apart. And yet, something is above the planets. Something is below them. Neutron stars live so far off the flat plane of our everyday experience that those familiar images stop helping and start misleading you. Here's the pattern interrupt. Your intuition is not bad. It's just overfitted. It was trained on low-density, low-speed experiments. Sand on a spinning table, water in a bucket, clouds rotating into hurricanes. None of that prepares you for matter packed beyond nuclear density and moving in orbits so fast that relativity quietly edits the script. In this regime, you can't rely on what feels too fast. You have to lean on the actual balance sheet of the forces. Gravity pulling in, centrifugal effects pushing out, internal pressure and nuclear forces locking layers together. Ask, what's the equation say? Instead of, does this feel reasonable? Because in neutron star territory, reasonable has left the building. And this is the bigger lesson hiding in the spin. Extreme astrophysical objects keep doing this to us. Black holes warp the idea of where things are. The large-scale structure of space shreds our flat solar system diagrams into a cosmic web. Neutron stars take our everyday sense of rotation, crush it down to 20 kilometers, and make us rebuild it from first principles. So as we push toward that claimed speed limit, toward the point where a neutron star really would start to tear itself apart, we have to ask a new kind of question. Not, does this look like a spinning ball? But what does physics actually allow? In the next part, we'll put numbers to that and watch where the universe finally says, too fast. So if the old spinning ball picture just broke, we need a new one. Not a tiny patch fixed on the side, but a full replacement for the star that lives in your head. Now let's begin with that calm, glowing sphere you've seen 1,000 times in textbooks. You know the one. Perfect circle, soft halo, just sitting there in space like a light bulb. Hold that in your mind for a second. Now start drawing arrows on it. Big arrows around the equator showing spin, smaller twisted arrows at higher latitudes, and a faint ghostly bulge around the middle where rotation is quietly fighting gravity. Because here's what nobody tells you. A star is not a static ball. It's a layered, rotating machine. The surface might spin at one rate, the deeper layers at another, the core at yet another. If you could peel back the photosphere like an orange, you'd see different shells sliding past each other, like a giant incandescent gearbox. So, let's start at the very beginning of that gearbox life. Way before there's a star, there's a cold molecular cloud, barely structured, just a slightly denser patch in the galaxy. It's not still. It has a tiny net spin. As gravity pulls that cloud inward, the same angular momentum is now trapped in a smaller region, and the whole thing speeds up and flattens into a rotating disk. Planets in our solar system inherit that, orbiting in roughly the same plane. A star is born at the center, with that spin baked in from day one. From then on, its entire life is a story of angular momentum being shuffled around. Stellar winds carry some away, magnetic fields tug on the outer layers, internal turbulence moves spin from the core to the surface and back again. But the total budget barely changes. When the core contracts late in life, it doesn't invent rotation out of nothing. It concentrates what was already there, like winding a spring tighter and tighter. Shrink a core the size of Earth down to a neutron star only about 20 kilometers across. And the only way to keep the same angular momentum is to spin unimaginably fast. Once you see that, neutron stars stop feeling like bizarre exceptions and start to look like the logical extreme of a pattern you already know. Of course, they spin hundreds of times per second. Of course, some millisecond pulsars tick at 716 rotations a second. That's just what happens when you take the ordinary rotation you've been ignoring and compress it until nature has no slack left. And yet something is above the planets. Something is below them. The same physics that quietly sets the solar system's orbital plane is also driving white dwarfs toward breakup speeds and whipping black holes into near light speed rotation. In the next part, we'll zoom back out, plug this new mental model into actual equations, and watch where the universe finally draws the line between fast and forbidden. So let's follow that thread and look at the other speed freaks sharing this cosmic racetrack. Because here's what nobody tells you. Neutron stars only look outrageous when you forget what white dwarfs and black holes are doing in the same gravity playground. Now let's begin with the slower cousin. White dwarfs are the exposed cores of dead stars, held up not by heat, but by electron degeneracy pressure. You squeeze the star, the electrons push back. They can spin, and some of them spin fast. But they're still about Earth-sized. Thousands of kilometers across, not 20. That bigger radius means that if you tried to crank them up to neutron star speeds, the outer layers would just lift off and escape. Imagine an Earth-sized sphere rotating so quickly that a point on the equator is almost in orbit around itself. That's the breakup limit for a white dwarf, where centrifugal force at the surface balances its own gravity. Push the spin faster than that, and the whole picture unravels into a cloud of escaping gas. So yes, white dwarfs can rotate in tens of seconds or minutes, but hundreds of times per second. Not if they want to stay in one piece. Now swing to the opposite extreme. Black holes. No surface, no crust, no solid anything. Just space-time itself, twisted into a whirlpool. Their spin isn't measured in rotations per second the way you'd time a pulsar. It's wrapped up in a dimensionless number, a fraction of the maximum angular momentum that gravity will tolerate before the event horizon would disappear in a tangle of relativity violations. You know the one, that famous A parameter that creeps toward 1. A rapidly spinning black hole drags the very fabric of space around with it, frame-dragging nearby orbits and shredding any hope of a simple, flat diagram. We infer those spins from warped accretion disks, from X-ray spectra, from gravitational waves when two of them collide. But we never see a black hole itself spin. There's no surface to watch, no lighthouse beam to time, just the shadow and the glow around it. Neutron stars sit right in the sweet spot between these two, compact enough that gravity can hold on at hundreds of rotations per second. Still made of matter, so there's a crust to fracture, a magnetic field to sweep a beam through space, a surface that can quite literally be torn off if the spin gets too aggressive. They're close enough to the brink that a point on the equator can move at a significant fraction of light speed, but not so far gone that they vanish behind an event horizon. And that's why they're priceless. They let us ask, in real time, how far you can push matter before gravity wins. How close can you get to the breakup limit before mountains melt? Superfluid slosh, and the whole star either sheds mass or collapses into a black hole. In the next part, we'll stop speaking in metaphors and plug these objects into the actual equations to see where nature really draws that line between fast, forbidden, and gone. So if neutron stars are playing this dangerous game with gravity and rotation, how do we actually watch them do it? We cheat. We turn them into clocks. Some of the fastest spinners, the millisecond pulsars, don't just flash, they tick. Their radio pulses sweep past Earth hundreds of times per second with such regularity that, over years, they rival the best atomic clocks we've ever built. In some cases, if you want to predict when the next pulse will arrive 10 years from now, you're better off trusting a dead star than the device that keeps global time on Earth. Because here's what nobody tells you. Once a neutron star settles into a clean, stable orbit, and its magnetic field calms down, the whole object becomes a flywheel of ridiculous precision. Every rotation is like a hand on a cosmic watch. We can predict pulse arrival times to microseconds, sometimes better, across distances of thousands of light years. That's like watching a spinning coin on the other side of the solar system and noticing if it slows by a fraction of a turn over a century. And that stability is exactly what lets us see when the act isn't perfect. Tiny slowdowns reveal magnetic braking as the star's field drags on its rotation and bleeds energy into space. Sudden jumps, called glitches, betray superfluid interiors that occasionally unpin and dump angular momentum into the crust. You get this eerie picture where every deviation, every late or early pulse, is the star whispering about the forces trying to keep it from spinning even faster. We're reading the error bars on a cosmic clock as a logbook of internal and external torques. Now, let's begin to really abuse that precision. If a single pulsar can be a clock, a whole network of them becomes a detector. Astronomers have built pulsar timing arrays, carefully chosen constellations of millisecond pulsars spread across the sky. The idea is wild. If a giant gravitational wave from a pair of supermassive black holes ripples through our region of space, it should stretch and squeeze the distances along different directions. The pulses won't change, but their arrival time will, by tens of nanoseconds. By comparing many clocks at once, we can turn the galaxy into a gravitational wave observatory. And yet, something is above the planets. Something is below them. In this case, the plane isn't the ecliptic. It's a timing plane defined by how perfectly these stars spin. The astonishing thing is that the more stable they are, the safer they are. A neutron star that can radiate steadily, break gently, and share its angular momentum over billions of orbits is less likely to tear itself apart in some catastrophic tantrum. But even the best clocks run down. These pulses will fade, the spins will slow, and that raises a deeper question. What happens to a neutron star that has spent billions of years flirting with its spin limits once the ticking finally stops? The ticking doesn't just stop, it stretches. It drags out over cosmic time until the neutron star's whole life becomes one long, slow goodbye to its spin. So, let's start at the very beginning. A massive star dies in a supernova. Its core collapses, and gravity slams a sun's worth of mass into a sphere the size of a city. Angular momentum has nowhere to go, so the newborn neutron star whips around dozens, sometimes hundreds of times per second. You know the one, the dramatic textbook picture with beams of light sweeping through space like a lighthouse. Because here's what nobody tells you. That wild newborn phase is already the beginning of the end. A strong magnetic field turns the neutron star into an enormous, rotating electromagnet. As those fields twist and sweep through space, they launch charged particles and radiation, and that outgoing energy acts like a brake. Millisecond by millisecond, year by year, the star pays for every flash of its beam with a tiny loss of rotational energy. Over millions of years, the spin slows. A pulsar that once whirled hundreds of times a second may crawl down to just a few rotations per second, then less than one. To us, that still sounds fast. To the neutron star, it's middle age. Its pulses grow weaker, its timing less frantic, and for many of them, this is where the story would end. Except sometimes, the universe cheats. If the neutron star lives in a binary, and its companion star swells and spills material, a new chapter opens. Gas forms a hot, bright disk in orbit around the neutron star, and as that matter spirals in, it drags angular momentum with it. Accretion doesn't just feed the star, it spins it back up. Over millions to billions of years, that slow, middle-aged pulsar can be recycled into a millisecond pulsar, ticking hundreds of times per second like a dead star that's found a second youth. Pattern interrupt. This is the part where you expect the spin to run away forever. It doesn't. Once the companion has been stripped or evolves away, the supply line shuts off. The millisecond pulsar is left alone again, blazing in radio waves and X-rays, now breaking much more gently. With a weaker magnetic field and a smaller beam, it can take billions of years to noticeably slow. And yet, something is above the planets. Something is below them. On these timescales, even the solar system looks temporary, while this tiny corpse quietly bleeds away its rotation. Give it long enough, and the pulses fade below our detectors. The neutron star cools, its surface darkens, and its spin drifts down to a lazy rotation, measured in hours. Extreme spin was never its destiny. It was a phase, a spectacular, over-caffeinated phase, but still just a way station on the road to a cold, dark, almost silent sphere. Because once you see that, you realize the universe always finds a way to cash out motion. The next question is how far it's willing to go to do it. So now we can finally zoom out and look at the whole picture. Why can these tiny stellar corpses spin so fast without just spraying themselves across space? It feels wrong. It feels like they're cheating gravity. Because here's what nobody tells you. Nothing about a neutron star's spin is random. It's all inherited, amplified and then sculpted by brutal physics. So, let's start at the very beginning. A massive star is born with some slow, dignified rotation. Over millions of years it burns, swells, and eventually its core collapses. When that core shrinks from something Earth-sized down to a ball 20 kilometers across, conservation of angular momentum slams on the cosmic spin button. The same gentle pirouette that once took days now happens dozens of times per second. And that's just phase one. In a binary system, the show gets louder. The neutron star can siphon gas from its companion, building an accretion disk that whirls around it like a miniature, deadly solar system. As that cloud of matter spirals in, it drags angular momentum with it. Over millions of years, that transfer spins the star up into a millisecond pulsar, ticking hundreds of times per second. You know the one, PSR J174824446 AD, rotating 716 times every second, with its equator racing at a decent fraction of light speed. So why doesn't that tear it apart? Because the interior isn't ordinary matter. The density is beyond atomic. Protons and electrons are crushed into neutrons, packed so tightly that nuclear forces dominate. The equation of state is stiff, which is just physics speak for if you try to stretch it, it pushes back hard. Gravity is immense, but the resistance of this nuclear fluid is too. Together, they create a configuration that can stay bound even when the surface is flung outward with absurd centrifugal force. What would shred a planet is just Tuesday for a neutron star. But there is a limit, and yet something is above the planets. Something is below them. In the same way, something spins these stars up, and something else always drags them back down. Magnetic fields act like invisible brakes, flinging energy into space as electromagnetic radiation. Gravitational waves leak angular momentum away if the star isn't perfectly symmetric. At the equator, rapid rotation can deform the star, pushing it toward the threshold where mass starts to shed. Inside, superfluid components can slosh and wobble, triggering instabilities that cap the maximum safe spin. Put all that together, and the observed spin distribution stops being mysterious. We see neutron stars that are fast, but not ridiculous. Extreme, but not infinite. The spin-up from collapse and accretion races against magnetic braking, gravitational wave emission, and internal instabilities, and what survives is a narrow band of allowed speeds. So when we say they spin faster than they should, what we really mean is faster than our earthbound intuition expects. Within the real rules of relativistic nuclear matter, they're not breaking physics. They're just showing you how far physics is willing to go. And that raises one last question. If we push a neutron star right to that edge, what breaks first? The star or our equations? So to answer that question, you need a new picture in your head. Not a flat diagram. A three-dimensional, spinning, evolving thing you can almost feel tugging on you with gravity. Start with an ordinary star. You know, the one from the textbook. Perfect glowing ball, politely minding its orbit. Now tilt it in your imagination and press play. The whole star is rotating. Not like a rigid billiard ball, but like a layered engine of angular momentum. The outer layers lag the inner layers, race ahead, hot plasma sliding and shearing past itself, magnetic fields threading through it all. Because here's what nobody tells you. Even when a star looks calm on the surface, deep inside it's already storing the spin that will define its death. Now, let's begin the collapse. Take that rotating engine and let the core run out of fuel. Gravity wins. The core shrinks from something roughly Earth-sized down to a sphere only about 20 kilometers across. In your mind, don't let it stop spinning. Let it spin faster, much faster. Like a figure skater pulling in their arms, except the arms are an entire sun's worth of material being crushed into a city-sized ball. That conserved angular momentum has nowhere to go, so the neutron star whips around dozens, then hundreds of times per second. A cosmic flywheel humming at the edge of what matter can survive. But the story doesn't freeze there. Put a companion star next to this whirling corpse. Picture gas peeling off, forming a glowing spiral disk around the neutron star, like a tiny, vicious version of the solar system's protoplanetary cloud. Every bit of that falling gas carries angular momentum. As it orbits in, it brushes the neutron star and twists it, cranking the spin up, click by click, over millions of years. This is how you get millisecond pulsars, corpses that rotate 716 times per second, surfaces racing around at a tenth the speed of light. How does that not just fly apart? That's the edge we were talking about. And yet something is above the planets. Something is below them. In the same way, something is above and below the old flat picture of stars we started with. Rotation, collapse, accretion. These aren't side notes. They're the main plot. Once you see stars as three-dimensional engines of angular momentum, you can't unsee it. Those neat static diagrams feel like lies of omission. So where does this new mental model finally break? If we keep adding spin, keep feeding the flywheel, what fails first, the matter or space-time itself? Hold that picture in your head, because that's where we're going next. So here's the uncomfortable part. We've pushed our mental flywheel to the edge. We've asked what breaks first, and the universe still won't give us a straight answer. Because here's what nobody tells you. For all our equations and simulations, the inside of a neutron star is still mostly a blank space on the cosmic engineering diagram. We don't actually know the true equation of state of ultra-dense matter. Is it neutrons all the way down? Do quarks melt into a strange quark soup? Does gravity squeeze in exotic particles we haven't even named yet? Each option predicts a different stiffness for the star, a different size, a different ultimate spin limit. Now let's begin to pull on one thread you can actually picture. Spin a dead star faster and faster, and it should start to throw off material at the equator, like mud flinging off a tire. Simple breakup calculations say that should happen somewhere above about 1 to 1.5 kilohertz, 1,000 turns per second or more. And yet, the fastest pulsar we've found is stuck at 716 hertz. Is nature quietly enforcing a hard cutoff there? Or have we just not looked in the right corners of space? Gravitational waves are the other big wild card. A slightly lumpy neutron star radiates ripples in space-time, bleeding off angular momentum. But how strong is that breaking in real life? Are millisecond pulsars secretly ringing like imperfect bells, held back by gravity waves we can barely detect? Or are they almost perfectly smooth with some other hidden break doing the work? Right now, the error bars are so big that both pictures can survive. So, let's start at the very beginning of our observational problem. We only see pulsars whose beams sweep across Earth's orbit. You know the one, the classic lighthouse picture with narrow cones of radiolite. If the beam misses us, the star is invisible, no matter how fast it spins. That means there could be ultra-fast pulsars out there, ticking above 1,000 hertz, and we'd never notice with our current surveys. Are we hitting a true wall in physics, or just a selection effect painted onto our flat sky maps? This is where the next generation of instruments turns the story from speculation into a test. giant radio arrays will trawl the sky for fainter, faster pulses. X-ray telescopes that can map hotspots on neutron star surfaces will pin down their radii to within a kilometer, slicing away whole families of dense matter models. And as gravitational wave detectors get more sensitive, they'll start eavesdropping on spinning mountains no higher than a grain of sand. One detection could blow the whole picture open. A pulsar confidently clocked above 1000 hertz. A razor-sharp radius measurement that makes every current equation of state look wrong. A continuous gravitational wave signal whispering that these stars are far more misshapen than we thought. Each of those would force us back to the whiteboard to rewrite what matter does under crushing gravity. And yet something is above the planets. Something is below them. In the same way, something beyond our current spin record is out there in the neutron star zoo, waiting. The next too fast dead star we catch might not just tweak the numbers on a chart. It could redraw the boundary between ordinary matter and whatever comes after it. So before we decide what the real limit is, we have to ask one more question. What happens when the star tries to outrun the very space-time it's sitting in? So that question is still hanging in the air. What happens when a dead star tries to outrun space-time itself? Before we chase that all the way to the edge, we need to lock in a new way of thinking about too fast. Because your old intuition is quietly lying to you. Think back to where we started. A city-sized star, maybe 20 kilometers across, spinning hundreds of times per second. You know the one. The kind of pulsar where a point on the surface is racing around at 1/10 the speed of light. At first glance, that picture feels impossible. Any normal object you've ever seen would just rip apart. Because here's what nobody tells you. Your everyday sense of what can spin and what can't was built in a world of weak gravity, low density, and very forgiving materials. It's like trying to judge the solar system from a flat poster on a classroom wall. The picture is familiar, but the physics underneath is doing something far stranger. So, let's start at the very beginning of our new intuition. We watched a massive star collapse, its core crushed from something roughly solar-sized down to a neutron star the size of a city. Angular momentum had nowhere to go, so the spin ramped up, the way a spinning skater speeds up when they pull in their arms. That's not a loophole in the rules. That is the rule. Then we layered on the second act. In a binary, a neutron star can steal matter from a companion, building an accretion disk that looks a bit like a tiny, vicious version of the solar system. As that cloud of infalling gas spirals in, it drags angular momentum with it. Over millions of years, that spin-up can turn a once ordinary pulsar into a millisecond pulsar, ticking hundreds of times per second. It feels like cheating, but it's just gravity doing accounting. We also saw the brakes, the breakup limit where centrifugal force at the equator matches gravity. The ultra-dense interior where neutrons behave more like a quantum liquid than a solid crust. Magnetic fields strong enough to grab plasma and fling it off. Gravitational waves quietly bleeding rotational energy into the fabric of space. All of that is why we don't see pulsars spinning at 10,000 times per second. Here's the pattern interrupt. Too fast is not a single number the universe respects everywhere. It depends on how much mass you cram into how small a radius, how strong gravity is at the surface, and what bizarre phases of matter you've unlocked in the core. Earth has one breakup speed. The Sun has another. A neutron star with a density beyond atomic nuclei plays by a different rulebook. So your new mental model should look like this. The universe is full of dead stars that can spin at mind-bending rates without breaking the laws of physics, precisely because those laws allow gravity and pressure to reach regimes we never encounter on Earth. In that sense, neutron stars don't spin faster than they should. They spin exactly as fast as their extreme conditions permit. And yet, something is above the planets. Something is below them. In the same way, above your old classroom diagram intuition, there's a deeper layer of astrophysics. And below it, there's an even stranger one waiting. Carry this upgraded sense of too fast for what with you, because this isn't the last time the universe will present a paradox that only dissolves when you zoom out and look at the full three-dimensional picture of gravity, orbit, and space-time. So now that we've rebuilt your intuition for spinning dead stars, we're finally ready to push it to the limit and ask, what if the star's rotation isn't just fighting gravity, but dragging space-time itself along for the ride? And if that image stuck in your head for a second, don't be surprised if it follows you to bed tonight. Because once you've pictured a dead star spinning so fast that a point on its surface is racing around at 1/10 the speed of light, held together only by gravity and nuclear forces, it gets very hard to look up at the night sky and see calm little points of light. You know the one. Oh, that quiet, peaceful mental picture of space as a still backdrop, a flat, gentle canvas with a few twinkling stars sprinkled on. Now you know that behind one of those dots, there could be a 20-kilometer sphere of ultra-dense matter rotating hundreds of times per second, dragging magnetic fields, plasma, and space-time itself along for the ride. How do you go back to thinking of the sky as empty after that? Because here's what nobody tells you. Once you learn that rotation can literally twist the geometry of space-time, it stops being just a number in an equation and starts feeling physical. What does it mean in your body for space-time to be dragged? If you could hover just outside a rapidly spinning neutron star, would around and above still mean what they do in the solar system? Or would your sense of direction dissolve as your orbit and the very plane you're in are pulled along by this compact, spinning corpse? Imagine trying to hover there and fire a rocket straight ahead, only to find that straight doesn't stay straight. That your path curves not just because of gravity pulling you down, but because the space-time you're moving through is being swirled like a cosmic whirlpool. Would you feel a kind of cosmic Coriolis effect? Would light itself seem to lean around the star as if the whole picture of space were being stirred? And if neutron stars can do that, what about the next level up? What happens when a black hole spins so fast its event horizon bulges, and the region where space-time gets dragged, the ergosphere, becomes a kind of one-way racetrack? What about magnetars, where the magnetic field is 1 trillion times stronger than Earth's, and the crust can crack in starquakes that ring space-time like a bell? Or neutron star mergers, where two of these objects orbit each other hundreds of times per second until they collide, launching gravitational waves we can literally record as tiny ripples in the length of a detector arm on Earth. If all of that leaves you feeling small, or odd, or a little unsettled, that's not a bug. That's the point. These are the moments when your everyday sense of scale breaks. When the universe quietly reminds you that the simple, flat diagram was never the whole story, and yet something is above the planets. Something is below them. So if this kept you up tonight, you're in the right place. This channel is where those late-night, mind-bending questions about gravity, orbit, and space-time don't get brushed off. They get unpacked, slowly, from the collapsing cloud to the spinning corpse of a star and beyond. In the next part, we'll show you exactly how we take that wild idea of space-time being dragged and turn it into something you can see, feel, and almost hear. Because once you've seen how far we can push gravity and rotation without everything flying apart, it's hard to look at a quiet night sky the same way again. Those calm points of light, some of them hide city-sized corpses spinning hundreds of times per second right at the edge of what matter can endure. So let's pull the whole picture together. Neutron stars can spin faster than they seem like they should, because 3 big engines are working in their favor. Collapse takes a normal star and shrinks it down to a 20-kilometer sphere, so conservation of angular momentum cranks the spin up to insane speeds. Accretion from a companion star keeps feeding them more angular momentum, recycling them into millisecond pulsars. And deep inside, exotic matter and superfluid layers help redistribute that motion so the whole object can keep whirling as one. But they don't just tear themselves apart, because here's what nobody tells you. The same gravity that crushed the core in the first place is now the only thing strong enough to hold this spinning wreck together, while magnetic fields, particle winds, and gravitational waves quietly bleed off energy before the star crosses its true breakup limit. That's why the fastest pulsar we've found spins at 716 times per second, not 10,000. Nature walks right up to the cliff, peeks over the edge, and then lets friction, radiation, and warped space-time tap the brakes. If you've stayed with us through all of that, from supernova collapse, to accretion disks, to superfluids and space-time ripples, that says a lot about you. You're the kind of person who doesn't just accept the flat diagram of a star's life. You want to know what's above and below that simple line. What's really happening inside those impossible objects. And we're genuinely grateful you gave your attention to this long, deep dive into extreme physics. If this reshaped how you think about how stars live, die, and spin, we'd love it if you'd like the video, subscribe, and share it with someone who still thinks dead star means nothing interesting left. Those simple clicks are how we keep making the kind of slow, careful explorations that textbooks rush past. Now let's begin the next layer of this story. If you want to keep following physics right to its breaking point, check out our playlist on black holes, supernovae, and gravitational waves. The places where collapsing clouds don't just spin, they punch holes in space-time itself. You know the one, the thumbnail with a distorted ring-like picture of a star being torn apart. And yet, something is above the planets. Something is below them. Somewhere out there, right now, a dead star is ticking hundreds of times a second. And our understanding of the universe is riding on every one of those rotations.